Hello, welcome to Next Generation Databases. My name's Guy Harrison. I'll be presenting for the next 50 to 60 minutes. Please feel free to ask any questions you like on the chat window, and I'll try and answer them if I can. Just to introduce myself, I started working with databases when I looked like this. At the time, people used to laugh at those glasses, but as it turns out, those glasses are a bit of a sign of geek cred. If you look at Bill Gates from the same time period, Michael Dell, we all wore those glasses and we all went on to great things, though perhaps I didn't go on to quite such great things as they did. However, I did work a fair bit in the database industry, written quite a few books on database technology, most recently Next Generation Databases and MongoDB Performance Tuning. And this talk is based on my book, Next Generation Databases. I'm CTO of ProvenDB and a partner at Toba Capital. And you can find me on the internet. GuyHarrison.net is the easiest way to find all things related to me. I'm also obviously on Twitter as Guy Harrison, LinkedIn, and there's my email address up there. So what I want to talk about is the changes in database technology that we've seen over the last decade in particular. Over my lifetime, I've really seen three database revolutions. So let's have a look at how databases have evolved over time. There have always been databases, even before there were computers. You can think of punched cards as sort of a database system. Libraries have indexes and information in them. But what we think about databases really emerged when the magnetic disk and magnetic tape was invented. And these technologies led to a bunch of early database technologies in the 1960s based on the hierarchical model and the network model. But then in 1970, Edgar Codd came up with the relational model. And it took a while for the relational model to take hold. But after a while, once Oracle in particular pioneered the relational model, we saw for a period of 20 years that every single database that emerged was a relational database based on the relational model, SQL language, and ACID transactions. But then starting around about 10 years ago, a whole new breed of databases emerged, and almost all of them were not relational databases. Things like Cassandra, MongoDB, and so forth emerged in sort of rapid succession. So why? Why did we suddenly get this third wave of databases? Well, the short answer is that we've seen three waves of application technology. The first wave were the mainframe applications. All the code ran on a single monolithic computer. There were millions of users worldwide and maybe thousands of apps. Then we emerged around about the time I started getting serious in the industry in the 80s. The client-server revolution occurred, where we started using typically Windows PCs as the client and some sort of mini computer running Unix or VMS or something with a database as the server. And this proceeded into the early internet phase. The early internet was basically still a client-server application. But as we got things like Facebook and Amazon, social, cloud, big data, we had a third wave of applications. And this third wave of applications required global scale and always-on availability. And the architecture of client-server just simply wasn't able to meet those needs. And as a result, we saw these new breed of databases come along to try and support the new breed of applications that we have today. Now, there are a couple of major trends involved in this third wave. I'm going to go through each of those in turn throughout the presentation, and then we'll see, maybe what's going to happen in the future. The first trend I want to talk about is big data, or as I sometimes like to call it, or O'Reilly coined this term really, the industrial revolution of data. So what we mean by that is that prior to the computer revolution, or the big data revolution, all data was kind of entered by hand. It was entered in-house. You had people literally who were punching the data inside organizations. It was even a job title, data punch operator, data entry operator. And that's where most organizations' data came from. But recently, we've had an evolution of the internet that's created the ability for data to come in from everywhere. And so here's an example just in our own lifetime. This is 2005, and everyone here is waiting outside the Sistine Chapel for the announcement of a new pope. And if you look at them, they're all standing around waiting. And right there in the center, you can see perhaps two people or one person has a mobile phone. But basically, everyone's disconnected. Now, let's jump forward just a few years, and another pope's being inaugurated at the Sistine Chapel. And this time, every single person has got a smartphone and everybody is recording and transmitting information. And so we've come to this situation where just in this short period of time, everything that can be connected to the internet is connected to the internet. Data is coming from everywhere. And that data is coming from social systems, from IoT devices, everywhere. It's even coming from ourselves. We are increasingly instrumented individuals. We're all carrying a smartphone, which has a local area network, Bluetooth, and a wide area network, Wi-Fi. It's got GPS and storage. A lot of us have got other devices that are connected to these phones, such as Apple Watches or other smartwatches. And a lot of us thought that eventually we'd have smart heads-up displays that would monitor even more. Now, the heads-up display, perhaps hasn't really taken off as expected. Back in 2012, I took this photo at Google I/O, and I was sick with envy at all these people with their Google Glass devices. So sick with envy that I tried to create my own, which didn't work out all that well, but still, I tried. But these devices didn't take off. But nevertheless, we are still, all of us, very instrumented. We're all producers and consumers of information. Now, the company that first had to come to grips with this big data revolution was Google. Right from the very beginning of Google's life, they had to deal with the exponential proliferation of websites. The number of websites that they had to index was growing at an exponential rate. And initially, Google this is Google's first hardware setup. It's just a bunch of servers under a desk. But pretty soon, of course, they had to evolve to proper data centers. And you can see there that the air conditioning is not quite working because there's a little fan down the bottom. But even this was not sufficient to cope with the exponential growth of demand. So Google went to a system in which they had shipping containers built with rack-mounted servers and dedicated air conditioning and power. And these shipping containers are full of commodity servers. Here's a guy inside one of these shipping containers swapping one of them out. There's so many of them, they're always failing and have to be replaced all the time. And Google's data centers are essentially big warehouses full of these shipping container modules of computers. And there are literally millions of servers in these shipping containers all around the Google data centers around the world. Now, it's astounding. This is really, 15 years old, and I'm still astonished by the scope of this hardware deployment. Now, obviously, Google couldn't use any off-the-shelf software to run on this hardware infrastructure. The hardware infrastructure was completely unique, and they needed a unique software layer. So they built this thing called Google File System that sat on top of all of the nodes and allowed the disks in all of these nodes to be accessed as if it was just one humongous file system. And on top of that, they used algorithms such as MapReduce, a massively parallel processing algorithm, some unique database technologies, and they built Google applications such as Gmail on top of this stack. Now, again, this is around 2005 that they established this infrastructure. They've moved on significantly since then. But what happened was that they published a lot of the details about this architecture, and the open source community took notice and built an open source equivalent of this architecture, which was Hadoop. And Hadoop was essentially an open source implementation of the core algorithms that Google had created. And Hadoop caught the interest of Yahoo, who were trying to compete with Google. And at that point, they were still, in the running, whereas now, of course, they really have fallen way behind. But they built out a huge Hadoop cluster to manage their search index. And in 2010, they had 4,000 nodes with 32,000 cores in a single cluster. And by 2014, they had 16 clusters with 32,000 nodes. So Hadoop got pushed into mainstream and battle tested very early on at a level of scale that open source technologies don't usually achieve. And as a result of this, a lot of companies got interested in Hadoop, and Hadoop saw some really, really rapid uptake. And primarily in the sort of data warehousing realm, of masses of data for analytic purposes. Now, the reason why there was seen to be a lot of promise in Hadoop was this idea of schema on read. So in data warehouses of the time, and this is still largely true today, you take some data and you have to extract it, transform it, and load it into a data warehouse. And this ETL process typically takes 6 months or so to achieve, and by then the data is stale and perhaps useless. And the idea was that with schema on read, you didn't have to do that right away. You just load the data straight into Hadoop, and then you analyzed it later. Only when you needed to. And this was seen to be a lot more responsive and a lot more flexible. And as a result of this, we got this idea of the data lake, in which all the data would be dumped into Hadoop cluster, and all of it would be there, whatever you needed, and you'd be able to build dashboards, do machine learning and analytics and so forth on it. Now, the data lake concept was quite simple. But there needed to be some embellishments on it, so people came up with more and more ideas of how to increase the complexity and capability of the data lake. And even then, that wasn't enough, so there was more and more complexity came on. So here's a data lake architecture diagram from, I guess about 5 years ago, and you can see how many moving parts are now placed into this sort of thing. And what happened, in essence, was this sort of beautiful data lake that everyone was dreaming of became more like a data swamp. Data went in, no one could get it out. Data became corrupted, it became smelly, it was just useless and not really very useful. And this sort of played out over the period of 2009 through to 2019. And really the data lake is still alive as a concept, but the Hadoop implementation has kind of failed. And there are 4 main reasons for this. Firstly, the data lake was too slow. Hadoop was able to store all this data, but not able to deal with queries in real time. Also, Hadoop didn't really solve the metadata management of the data. There was no sort of built-in catalog, no way to sort of like record what had gone in and how to get it out. There was a shortage of data scientists who could leverage all this raw information and turn it into competitive advantage. And there were lots of, as companies migrated into the cloud, there were lots of cheaper solutions than Hadoop. And so these solutions, things like S3 buckets became more competitive against Hadoop, and Hadoop really failed to transition to the cloud. But however, during that transition to the cloud, not everybody, but a lot of people realized that what was needed was some sort of hybrid between the concept of the data lake, the elastic storage, the ability to deal with unstructured data, and the data warehousing world of powerful SQL queries, massively parallel, real-time abilities, and so forth. And so we've seen a bunch of SQL data warehouses return, the most notable of which is Snowflake. Now, Snowflake is a data warehousing system that is built natively for the cloud. It's capable of dealing with relational data, but also with unstructured data in JSON and flat files. And it's capable of dealing up real-time analytics as well as machine learning and other sort of like analytic workloads. It's, as I said, it's native to the cloud. It's capable of elastically scaling to take on cloud resources in a very cost-effective way. And these advantages led to Snowflake last year having the biggest ever software IPO. So certainly the market has responded to Snowflake's concept very positively, and it's now one of the most highly valued software companies in the world. So we saw sort of big data sort of go through a fairly natural phase of coming back pretty much to SQL relational systems after a sort of like a little detour into the world of Hadoop. But the other trend that was very relevant during the same period is what we typically call NoSQL. And of course, when we said NoSQL, we didn't mean NoSQL, as you'll see. So often NoSQL is now taken to mean not only SQL. So how did NoSQL come about? Well, to understand this, we've got to go back a little bit further and look at the early web architecture. So typically the simplest kind of web application has a web server and a database server at the back end. And if you need more load, or if you've got more load, you would add more web servers. And if the database became a bottleneck, perhaps you could add some caching servers. This is very popular back 15 years ago to add these things called memcached, which were sort of like in-memory caches of data that could feed read-only data very quickly. If the database itself continued to get a bottleneck, we might create read-only slaves using replication. And if the database really still bottlenecked on writes, then we would shard. We would split the database up into multiple copies. And so these copies might have, broken up by username, A to F in one shard, G to O in another shard, and P to Z in the final shard. And the application would need to know how to sort of like navigate all of these bits and pieces. Now, this architecture is operationally obnoxious. It's so difficult to deal with, but it's also broken the relational database system that we knew and loved so well. You can't have transactions across these shards. You can't do joins across the shards. Really what's happened is you've taken the relational database and you're just using it as a sort of like a file server. And it's the middle layer, the sharding layer, that's got to do all the data processing logic. And at about the same time, people began to realize that there really was a very significant fundamental reason why the databases of the day couldn't handle the demands of this sort of third wave of applications. And that was CAP theorem, or sometimes called Brewer's theorem. And Brewer's theorem says that you can only have 2 out of 3 of consistency, availability, and partition tolerance. So you can be consistent and available, or you can be available and partition tolerant, but you can't be all 3. And so relational databases tend to be consistent and available, but unable to deal with network partitions, whereas the new breed of NoSQL databases, as we'll see, decided to be partition tolerant. Now, Brewer's theorem and CAP theorem sound a bit complicated, but really the concept's very simple. So let's say that we've got an application. We've got some of our servers in the US and some of them in Australia, where I live, and they're connected by the internet. And I've got a user in the US and a user in Australia. What happens if the network between Australia and the US is severed from some reason? Well, in a normal relational database cluster, such as Oracle, for instance, one side would go down and probably be the Australian side. And so people in Australia wouldn't be able to do anything. And that's fine for some applications, but companies like Amazon didn't like this solution. They wanted the users to continue to have the system available, even if the system was split in 2. They'd rather have people in Australia continuing to buy things, even if they were seeing slightly out-of-date prices, or even if they couldn't read the whole catalogue. So this network partition in the Amazon world, they wanted to build a database that could still maintain availability in the face of this network partition. And they built this thing called Dynamo. And Dynamo works by spreading the data across all the nodes in the cluster. And so let's say we've got a cluster with these 9 nodes, sorry. And each node is responsible for a certain range of hash values. If we put a new piece of data in, we hash it. That tells us where its first copy goes. And then it's replicated to 2 other nodes in the cluster. And we can get a little bit more complicated than that. We can set rules such that it's replicated to 2 other nodes that are in different racks, or even in different data centers. So in this case, we could make sure that it was replicated to Australia, for instance. Then we have this idea of a tunable consistency model. So we're always going to write, in the simplest case, 3 copies of the data. But how many copies have to be written before we can return from the write? So for instance, we can say that we want to write just to 1 node. Now they'll all be written later on, but for now, as soon as the first node is written, we consider the operation to be a success. But when we read from all 3 nodes. And this makes sure that we're always going to see the most recent piece of data. It means that reads will be slow, but writes will be fast. Now we can go to something sort of like a middle range where we write to 2 nodes before the write returns, and we read from 2 nodes. And that also guarantees that we're going to see the most recent piece of data, and it more balances read and write performance. Or we can write just to 1 node, and we can read just from 1 node, in which case reads will be fast, writes will be fast, but we might see out of date data. And between these sort of consistent hashing policies and these tunable consistency models, we get a great deal of control over how consistent we are versus how performant and available we are. Now, this sort of Dynamo model was adopted by a bunch of open source systems as well. Cassandra in particular works with this model. React is one that also worked with the model, but has gone under now. And so there's a lot of NoSQL databases that are using these sort of Dynamo models. However, there's a lot of unhappiness about the idea that data might be inconsistent. And at Google, the researchers decided that they wanted something a little bit different. And they had a different idea, which was, what about instead of giving up consistency, we tried to minimize network partitions? So they're saying that, okay, they accept CAP theorem, but they would rather be consistent and available. And they want to do that by just trying to reduce the network partition probability to almost nothing. And how they did this was by leveraging Google's highly redundant internal network and using onboard atomic clocks for transaction synchronization. So Google has this network around the world where every site is linked to every other site by at least 3 network links. So they're saying that the idea that Australia might be separated from the US is very unlikely. So unlikely that we don't need to worry about it. So we won't sacrifice consistency in order to preserve network partition tolerance. What we'll do instead is we'll make network partition tolerance really, really unlikely. And the other thing they do here in this distributed system is that they have, all the servers have a very, very good idea about what time it is down to the microsecond. Because when we've got transactions coming in a highly distributed system like this, it's very important to know what order they came into in order to preserve consistency. And Google does this by having GPS and atomic clocks in each data center that allow for a very, very tight clock skew. The discrepancy between clocks on different systems is very, very low, which means that they can be very, very certain about the sequencing of transactions. Now, Google's Spanner architecture has inspired a bunch of open source technologies, such as CockroachDB, TiDB, and UGabiteDB. These are all distributed SQL systems that are really taking NoSQL, giving NoSQL a run for its money. They're SQL relational systems that they're not exactly partition tolerant, but they use all of the tricks from Spanner to try and make a distributed SQL system that can work with modern, high available, globally distributed workloads. There's another advantage of distributed SQL, and that is that they're very compatible with containerized application architectures. So to understand containers, that you probably already know about Docker and Kubernetes, but I'm just going to run through the evolution of these architectures anyway. So you remember early on I said that we started with the mainframe, and in the mainframe, the application and the database sit together in the one physical piece of hardware. And then we went to client server, where we split the hardware up into 2 chunks, one with the server, which was really mostly just the database, and the client, which was where the application logic lived. And then in the early internet was really client server with a web browser tacked on to the architecture. And that took us through from the 1960s through to the early 2000s. Around about the 2000s, there was a lot of work done on virtualization, where we take these components and we would stick them in we would create them in virtual machines so that we could share hardware resources more effectively. But it didn't really change the architecture. It just made the physical machine become virtual. But then the next wave or the evolution of virtualization led to container architectures, in which application code was broken up into microservices. Those microservices would run within their own Docker container, and Kubernetes or similar orchestration layer would coordinate the creation and failover and load balancing of these Docker containers to provide a coherent application framework. And Kubernetes and Docker, for someone of my age, are absolute miracles because they allow us to deploy complex distributed architectures so simply compared with the blood, sweat, and tears that used to happen when we had to build out distributed architectures on physical machines. But when we're talking about monolithic database systems such as Oracle or similar systems, or MySQL or non-distributed databases, they can't really work within the Kubernetes framework. You can't take these databases and turn them into an arbitrary number of Docker containers. They have to run as a single entity. They might be in a Docker container, but you can't have multiple, so they don't scale very well. But these new breed of distributed SQL systems, such as CockroachDB, they do work within Docker containers. And so now these distributed SQL systems, and to be fair, distributed systems such as Cassandra are very compatible with Kubernetes and can allow us to have a completely modern Kubernetes-based application stack that includes the database. And that's, I think, going to be increasingly important going forward. Okay, so the next trend, or the next driver for next generation databases were developers themselves who wanted a resolution between the object orientation of programs and the relational model, or who just really didn't like alter table because it broke continuous integration. So some developers, at least, have always hated SQL. SQL and the relational model required that beautiful object-oriented program structures had to be broken apart and placed into tables, somewhat like taking a car and driving into a garage and then having to disassemble it and reassemble it every time. SQL statements in code are also very ugly. They're sort of like long text strings that are awkward to write, test, and maintain. And with relational database schemas, they didn't work very well with continuous integration. If you have to have an alter table statement that has to run against the database during a continuous integration pipeline, then it's really difficult to coordinate that. Whereas, what you really want is to have all the schema definition within code so that you can just, commit your code to Git and have the application build and any changes sort of automatically propagated. So this led to a set of databases that are typically called document databases. And a document database, instead of decomposing objects into multiple tables into third normal form, we just store it as a object itself, usually as a JSON object. So there are Couchbase and MongoDB being the most widely used JSON documents. The only object or the only sort of schema is JSON itself, the ability to store something as a JSON object. And so MongoDB has been enormously popular with developers. This is old data, but 30 million downloads a couple of years ago. You can see the popularity of MongoDB on Stack Overflow. And MongoDB has been very successful at creating a sort of like a familiar experience. So this is, for instance, a MongoDB query written in its aggregation language, and it's roughly equivalent to this SQL statement. So MongoDB is very functional, very capable, and very popular. And it's probably it's of the top 5 databases, it's the only one that has been built in this century. However, it's important to realize that all the SQL databases now support JSON as well. So you can store JSON documents in all of the major relational databases, Postgres, Oracle, SQL Server, and so forth. And also, all of the NoSQL databases now support SQL. So there's always some way, if you want to use SQL against a supposedly no SQL database, that you can do so. So there's a lot of convergence going on here between the document database world and the SQL database world, and it's not clear where this will end up. It may be that the distinct category of document databases will disappear and it will just be a feature within databases. One other category of NoSQL I wanted to mention briefly was graph databases. This is really a niche. Graph databases aren't trying to replace databases as a whole, but they're very, very useful when you want to record the relationships between things, such as in social networks and similar situations. So here we see a graph database that's tracking actors and movies. And if you want to find out who co-starred in movies together, this is a great way to do it. And the two most popular, or the two ones I'm watching anyway, are Neo4j and TigerGraph. So another category that or another trend that I want to briefly touch on is the fairly obvious fact that cloud databases have hit a tipping point in the last couple of years. Or another way of putting this was Larry was wrong. So what do I mean by Larry was wrong? Well, Larry Ellison, CEO of Oracle, in 2009 famously ranted about clouds and said that they were nonsense and it's gibberish, it's insane. And for a little while, people, at least in the database community, were very complacent about the cloud. Databases seemed to be moving into the cloud slower than everything else. And the reason was logical, if you think about it. There were two downsides to moving databases into the cloud. So if you just take a database and move it into the cloud on its own, you've opened up the database to the external network, making it vulnerable to security attacks. And you've created a longer round trip time between the application and the database. Both of these are bad things. But once applications moved into the cloud, these two advantages disappear. Sorry, these two disadvantages start to disappear. And now we're finding that most applications are in the cloud, and so most databases want to be in the cloud as well. And when you look at the growth of databases, you see that the cloud native databases are all showing very robust growth. And all of the traditional databases are going cloud first, which is to say that the major database vendors are trying to get you to use their cloud services in preference to their on-premise offerings, partially because there's a very good business model for working with cloud services. You can't run an open source version. You can run an open source version of the software on premise and pay nothing, but once you're in the cloud, you need to pay a fee, which is why MongoDB is particularly happy with the rate of cloud adoption. But I would point out there's cloud databases and then there's cloud databases. So it's not enough just to take an on-premise database and put it in a VM in the cloud. That is not a real cloud database, at least not the way I think about it. A lot of what Amazon offers in RDS are really just normal databases running in a virtual machine on the cloud. There are scalable databases running across elastic cloud infrastructure, even if they're designed to run on-premise, if they're a clustered database, Oracle RAC, for instance, and they're placed in a cloud infrastructure where you can elastically scale them, then that's better. It gets even better if the database is fully managed. And by that I mean that there is no DBA tasks, or very few DBA tasks need to be done. Backups, security, scaling is all handled automatically for you. And then, but even better are the cloud databases that were built from the ground up with the cloud in mind. And these are the ones typically that have emerged in the past 10 years. Nothing developed in the 1990s or 2000s could possibly be considered to be cloud native. It's more things like CockroachDB, Snowflake, things like that are cloud native databases. So we've talked a lot about how things have been sort of like new technologies in databases have come about. Now I want to talk about the opposite trend, which is convergence, the degree to which all of it is trying to be pulled back together. And I'll subtitle this one as The Empire Strikes Back, because back at the Death Star, which is what I affectionately call Oracle headquarters, the emperor of databases was aware of all these strange new disturbances in the database force and was determined to strike back. So Oracle's been working very hard over the past 10 years, or forever really, but particularly in 10 years, to add everything into the Oracle system that we've been talking about. So there's an Oracle Big Data Appliance, which is essentially Hadoop in a Exadata box. Oracle's got strong JSON support. Oracle's got a graph database built in. Oracle has its own breed of NoSQL database. Oracle has sharding now, and Oracle has a cloud offering. And a lot of effort has gone into doing all this in Oracle. However, unfortunately, I think their problem is that nobody cares, or at least developers don't care. So if you look at Stack Overflow popularity ratings of databases, you'll see that Oracle is the second least loved and second most hated database. And this reluctance for developers to even consider using an Oracle database makes all of these convergence efforts fairly ineffectual, because unless a developer is willing to take on these new features, they're not going to get much traction. Also, Oracle's efforts are a little bit disjointed. I'm much more impressed by what Microsoft have been doing with Cosmos DB. Now, Cosmos DB is not a very widely used database, but it is a cloud-native database that runs in Azure. And as you can see up the top, it supports all the different sorts of interfaces that you might want. It's MongoDB compatible, Graph compatible, Cassandra compatible, and it supports all the different types of data models that you might want. And it's got a sort of like a high availability mechanism, similar to Spanner in some respects, with a highly redundant network and so forth. So it's a very impressive technology. It's kind of a bit too much trying to be everything to everyone, probably. And so as a result, it's sort of like not hitting any particular niche particularly hard, but it's definitely one to watch in terms of convergence. All right, so I'm going to start sort of like moving from things that I know to things that I'm speculating about. And I'm just going to talk for a little while about possible disruptive technologies in the database space. So firstly, universal memory. So we have always had, since the very earliest days of digital computers, multiple tiers of storage. So we've got magnetic disk, and today we've got sort of like spinning magnetic disk and flash disk. So we've got two layers of persistent storage with different performance and price characteristics. And we've obviously got RAM, which is not persistent, but it's very fast but expensive. And we've got registers within the CPU. So each of these four layers effectively run at different speeds, have different costs, and have different persistence characteristics. The dream in computer science is to create a single technology that would be as fast as memory and as cheap and persistent as disk. And if anyone ever created this sort of universal memory, it would completely eliminate the architectures that almost every database uses. So there's always in database architectures this idea of memory versus disk, persistence versus high-speed access. And so this sort of perennial quest to build universal memory is very important for databases. Now, one example of this is 3-point memory media, which sort of like perpetually claims to be moving close to this ideal. As yet, I don't see anyone coming close enough to warrant a sort of redesign of all database systems, but it could happen, and if it does happen, it'll change. We'll need a whole new breed of databases. The second disruptive trend I'd like to talk about is blockchain. And I'm going to go on an even more sort of like long-winded history lesson to talk about blockchain. So we've been storing data on media for something like 10,000 years. This is a cuneiform clay tablet with kind of accounting records from about 5,000 BC. And we've used other things, there's been stone. But for most of human history, it's been paper where we've stored our data. And all of the three technologies we've looked at so far seem primitive, but they have the advantage that once you've written something down, changing it becomes hard to do without leaving some sort of a trace. If I take this ledger and try and scratch out one of the entries, I'll leave some traces of my efforts. I could tear the whole page out, but that would leave a trace. People do cook the books, of course, and always have. But these primitive technologies do have the advantage of leaving traces when things have changed. But of course, in the 1950s, we invented magnetic disk, and here's the first 5 megabyte magnetic disk. Here's the 5 megabyte magnetic disk being placed on a truck. 5 megabytes used to take 4 big guys to move around. So it's like amazing to think about 5 megabytes weighing a ton, but there you have it. Disks got smaller and faster, and of course we moved to solid state disks recently. But they all have this one characteristic, that anything that can be written to the disk can also be overwritten without a trace. And no matter what you do, this leaves you vulnerable to tampering and fraud and destruction. And so our entire sort of civilization is currently based on these electronic records that could all disappear or could all be falsified. And there's enough false news and document tampering in the news to understand how this is a concern. Now, blockchain is a technology that's often mentioned in this context as being a possible solution to this problem. Blockchain is able to do trustless transactions and immutable data recording. So why is that? I could go into the technology of blockchain, but I'll just say simply that in a normal currency transaction, you have data moving from one bank to another. Business A sends a payment to its bank that sends the transaction to its another bank, and then it goes up to the first business. And there's these banks that are sort of actually doing the transfer between one party and another. But in cryptocurrency, all of this is replaced by this blockchain, which is this record of all of the transactions that go through between these two entities. And this blockchain record is immutable. It can't be changed by known technologies, or at least not without absurd amounts of computing power. So for the first time in computer science, we have in the blockchain something that when we write to it, we can be certain that it isn't overwritten. And this is massive. But unfortunately, the blockchain itself isn't a database. It's like it's got very high latency and low throughput. It's got a very limited data storage capacity. Transactions are anonymous, but they are public. There's no schema or data model in there. It costs money to do transactions, too much for most people, and it's not a very productive environment for developers. So this has been a dilemma, and you'll see since blockchain became a thing, people saying, should I use a blockchain or a database? And if I use a database, I'm sacrificing immutability and tamper detection. But if I use a blockchain, I've got no performance or economics. And you'll see, do blockchain versus database, and you'll see all this sort of chatter about it. So most of the time, the answer is use a database. It's unusual that you need such a level of security for to use a blockchain instead of a database. But there are some blockchain databases that can offer a compromise between blockchain characteristics of immutability and database characteristics of performance. I have to warn you, my day job is at ProvenDB, and that we build a blockchain database. Here's ours. There are also offerings from Amazon, Flurry, BigChainDB, and Oracle, and rumors Microsoft are also building blockchain databases. So this is an area where there's a lot of innovation. We probably see blockchain characteristics introduced into most database systems over time, and this will cause a lot of fundamental changes. Okay, and now my final disruptive trend, quantum computing. So how does quantum computing affect databases? Well, it affects databases by virtue of affecting pretty much everything we know about computing. So in a normal computer, all information is held in bits, and a bit can hold a 0 or a 1. So if you've got 1 bit, you can have a 0 or a 1. But if you've got 1 qubit, which is a quantum bit, it holds a kind of superimposition of 0 and 1, which means, if you like, it's holding 0 and 1 simultaneously. Now, if you had 3 bits, you could hold any number from 0 to 7. The 3 bits can, 001 is 1, and 111 is 7. So if you've got 3 qubits, though, you can hold and process every number from 0 to 7 simultaneously and process them immediately and identically. And so a 64 qubit quantum computer could hold and process that number there, 18 to the whatever numbers simultaneously, some 18 trillion or something numbers simultaneously. Now, the basis of all database systems is the storage of bits of information. If quantum computing truly becomes mainstream, we're going to need some sort of persistent storage system that can handle and store the results of qubit operations. We're going to need some sort of quantum database. And honestly, I think we're still in the industry struggling to think about what that could possibly mean. But as with all things, quantum computing would change everything. If we get a working 64 qubit quantum computing, we'll need to change encryption and all sorts of things. Now, quantum computing sounds very science fiction, and that's because it kind of is. How does a 64 qubit quantum computer process all of this data simultaneously? Where's the parallelism coming from? Well, one broadly accepted way of physicists understanding this is that it's happening in parallel universes. So one of the precepts of quantum computing is that when a decision happens at the quantum level, both things occur. We only live in one of the outcomes. But so here, someone's saying, would you like to go for a drink? And in one case, the woman's saying, I'm too tired. And in the other case, she says, sure, why not? And in one universe, they marry and have kids. In the other universe, they're on the other side of the world. And a lot of physicists believe that there are these sort of multiple quantum realities occurring all the time, and that the reason quantum computers work is because they can process data in all of these parallel universes simultaneously and combine the results back in our universe. Now, that's mind-boggling and amazing. All I can say to you is that at least in one of those universes, you all enjoyed my talk. In other universes, you probably didn't. I hope I'm living in the universe in which my talk went well. Thanks very much for attending. This talk has been recorded and I'm going to be online simultaneously to answer any questions that you may have. Thanks very much. Have a great conference.